Okay, and so our second speaker is Anthony Macherone from Agilent Technologies, and he's also has an appointment at the Johns Hopkins School of Medicine. And so Anthony is, I believe, is a collaborator with Steve Rutherford. He mentioned his work and collaborations in the previous session, and he's also the chair of the Exposome Interest Group at the American Society for Analytical Spectrometry, for mass spectrometry.
Okay. So, I'm going to talk a little bit today about detection challenges, and I did kind of struggle with this topic a bit. So please feel free to be brutally honest and critical with me afterwards. I appreciate that, and you don't have to be politically correct or kind. I'm happy to get the full brunt of your criticism. So really, I had to say to myself, after really thinking about it, what is detection? What is it all about? And, from kind of an instrument or the detector perspective, there's really a lot of parity across vendors. There's a single quad from one vendor compared to a single quad from another. It's very similar. There might be different features, but at the end of the day, their detection levels or what's stated specifications of limits of detection are going to be very, very similar. So it really, you shouldn't think about those types of things when you're thinking about detection. And it's really more about how we utilize the system, how we look at the system holistically, and we implement the methods with our real samples. That's what detection really starts to come down to. So it is this ability to differentiate the real signals from the din of noise. So there's lots of things happening in our samples, in our chromatograms. How do we make sense of that? How do we understand what's real and significant from the things that are normal variation or background noise? And we need to be able to do this both from a qualitative and a quantitative perspective. And we have to do this, most importantly, with reliability, precision, and confidence in my answer. So how do we go about those types of things? So again, it's more than just the detector, and we have to kind of look at these things holistically. So what are the factors that affect detection? And I think you have to think about your samples, and we'll talk a little bit about that. I'm not going to focus too much on that, but the samples and the way they are prepared will dictate what you see or what you detect in the end. The analytical platform. Which one should I use to answer this problem? There's lots of different tools out there. What's the appropriate one to answer the questions that I have? But I think where I'll spend most of the time is really the application, the methodology. To measure the exposome, we need to measure many disparate chemotypes. We want to do this simultaneously. We want to collect lots of chemical information as rapidly as we can from the samples that we have. And so this is a very difficult thing, and maybe counterintuitive to what a lot of people have done throughout their analytical chemistry careers, where they're focusing on targeted analyses, quantitative, very rigorous, validated type studies. Now we want to move into something where we're really looking at broad spectrums of information. And most importantly, again, with this, we need to consider how do we take all of that information and turn it into knowledge? And that is where the bioinformatic tools, qualitative, quantitative tools that we have come into play. So just quickly on the samples, there's lots of problems. A lot of them have been alluded to today, how they were collected, how they were stored. They're listed as a lavender top or EDTA type tube, and it wasn't. There was heparin in there. We don't know. And how do you curate those types of things? And there was actually a pretty clever way of maybe pre-screening everything with your NMR. That way, it's not going to get to your mass spec, and that might keep your uptime on your mass spec. So that's a pretty clever way if you have that opportunity in your laboratory. And another real problem is you're not going to get a lot of samples. So you're going to get a couple hundred microliters of sample. How do we deal with that? How do we how do we disseminate that across a number of platforms? How do we get the most information out of these small volumes? So those are some common issues that you'll run into with your samples themselves. Then how are they prepared? And this really dictates what you're going to see in the end. The way you do an extraction will, you can do a Bly dye, look for lipids. You can do other types of extractions. I think one of the proposed methods, and possibly one of the more common ways, is really take your sample, protein crash, spin it, dry it, reconstitute. Don't manipulate it that much. You want to try to retain everything that's in there and not lose too many things. But then again, there's other schools of thought that could be much more rigorous in terms of sample prep. For example, I know from personal experience that if you really want to measure that part of the curve of persistent organic pollutants that are much less concentrated in blood, you will have to do a much more rigorous extraction methodology to see those things. So the analytical platform itself, well, electrospray doesn't do everything. And, I'm happy to see that there's a pendulum that was swinging to, we can answer every question with electrospray, and it's kind of coming back to say, okay, we absolutely have to have, EI, gas phase, chemical ionization tools, APCI, other tools in our laboratory to really answer these complex problems. So not one technology is all-encompassing, and we have to leverage the pros and cons of each of these technologies. And what can I afford in my laboratory? What's available to me in my colleagues' laboratories? Is it reliable or accountable? I mean, am I going to get an accurate, specific, precise answer with confidence off of this platform? And you want something for the exposome, I think, that can measure a broad range of the chemical space. Now, that happens to be, I think, electrospray, but you need to have these other tools as well. So you can kind of estimate what these, what the coverage of these detectors will be. And we kind of have the exposome space here on the y-axis, and ICP-MS, obviously, I think is an important tool for complex metals, organohalogens, things of that nature. Of course, NMR, GCMS. There's lots of overlap with all of these. And of course, I think, NMR can be used very broadly. So you could actually have a lot of overlap here with the NMR. So these are some of your common platforms that you might engage in your work. And so what do we have? I think, with LC technologies, I think, as I said, there's lots of breadth that can be covered there. Electrospray positive, negative, Hillick, reverse phase. This can cover a great deal of the exposome space, and it works probably best for small polar compounds that have lots of nitrogens, oxygens on them, things that can pick up a proton or lose a proton. A good rule of thumb of that came from Lipinski's rules of the number of hydrogen bond donors or hydrogen bond acceptors. You can kind of look at that and almost predict whether a molecule will respond to electrospray. It does, there is matrix suppression. There's other issues with that as well. Of course, GC technologies, EI, there's large libraries commercially available. This is probably the oldest technique that's been out there, so there's lots of information available commercially to search libraries, screen your data through to try to identify what you're observing. Of course, chemical ionization and APCI can be very, very useful. You can take advantage of negative chemical ionization, for example. You can tailor your derivatization chemistry to look for specific chemotypes or functionalities within molecules, and then really leverage the power of negative chemical ionization to get very sensitive quantitative and some qualitative information. And then, of course, the NMR, which is nice because there's really no method development on NMR. Put it in your deuterated solvent, mix it up, put it in the magnet, and get some information. So it covers a lot of space. It's very specific, but I think, as we noted in that previous graph, there can be some issues with sensitivity. So the challenges in detection really come down to how you create your method, the methodology challenges. And there's lots of things that can, happen here. Am I going to use a data-driven technique, knowledge-driven technique, semi-targeted methods? Which and when? Should I combine them? How should I, implement these types of tools? Accuracy and precision, sensitivity and selectivity. I think these are probably the major things that one should be concerned with when they're going to measure biological samples. But there's other challenges as well. Dynamic range, not only concentration dependent, but the in-spectrum dynamic range. What are those little ions, at 100 counts? And can I see them in conjunction with things at 1 million or 10 million counts? I want to be able to see those types of differences in my in-spectrum dynamic range. So just to kind of talk about what briefly these data-driven or knowledge-driven or semi-targeted type methods, what they are. The data-driven are really discovery type techniques where I'm going to build what I used to call a very generic method, maybe a C18 column, very formic acid and water type modified buffer system. And it's going to cover a lot of breadth of very much of the chemical space, very many different chemotypes. It's not going to do everything perfectly, but it's going to do a lot of things fairly well. And so you can implement these types of things, collect a lot of information very quickly, but it may have trouble with this part of the curve that we mentioned earlier, where the persistent organic pollutants lie in blood. So then we have our knowledge-driven, which are targeted methods. These tend to be validated methods that more rigorously developed. And these will be your most sensitive, especially if you're going to use MS type techniques. And then you can combine these two, obviously, and have something where, say, on a QTOF type instrument with data-dependent MS kind of going on, you could actually combine these, screen for all of your unknowns, but also target specific other compounds that you can look at in a quantitative sense. And so you may have 50 or 60 compounds that you want to look for, you want to quantitate, but you also want to be able to interrogate that data for everything else that's in there. So that's kind of the semi-targeted way of doing things. So continuing on with these kind of methodology challenges, the accuracy and precision, and we'll talk a little bit about this in terms of the untargeted qualitative type analyses, these data-driven type analyses. They're typically not validated. And I think if you really want to do this, I think it's important to kind of, as you're developing these methods before you get into quote-unquote production mode, you want to be able to determine a set of analytes. It could be 5, 10, it could be 50. It really doesn't matter, but they should be chemically diverse, cover a broad mass range, and fixed set of compounds that you can monitor over time to characterize the performance of this method. And this performance standard then can be used when you're actually looking at real samples. So interspersed throughout your sequence, you're measuring this performance standard. It must meet certain defined metrics, retention time precision. If you have, say you're doing SIM or scheduled MS, you want to make sure everything's where it needs to be, that you're seeing everything as it should, and those metrics are being passed. And this can provide a traceable measure of confidence in that analytical method. It can also provide you information that you can use for a historical perspective when you run into problems. You know how that standard should behave, you know how that should look, and when problems happen on your instrument, you can immediately refer back to that and say, okay, is it my chromatography? Is it is the detector dirty? Those types of things. And with time, you'll begin to understand that method very, very well and have a way that you can go back, review what's happening, and fix it very, very quickly. So you can also do that, I think, with, obviously with targeted methods, which tend to be, as I mentioned, much more validated type methods. More time is put into those. They're going to be something that you use day to day, and you really want to have rigorous quantitative ability in that method. But again, during that method development phase, you want to define this set of standards. Now they can be called quality controls that you monitor over time that will characterize the accuracy and the precision of your method. And as you run your samples, these things are bracketed around your unknowns, and they're run often, and they must, again, pass these definable, quantifiable metrics. And this, again, will give you confidence in your analytical tools that it's working as you think they should. So specificity it really is about taking high mass accuracy, high resolution, can give you the ability to distinguish what you're interested in from the background noise, from the matrix, from other compounds that will be in there. You can also take advantage of MS processes to differentiate the signals that you're interested in from those that you're not. And this targeted or semi-targeted analysis might be needed in conjunction with discovery methods or used solely to cover, again, this POPs exposome space, which I, as you probably can tell, have an interest in. So in terms of specificity, you can say lowest on this is your single quad instruments. You can do scans, SIM will get more specific. MS is even more specific. Of course, high-res mass spectrometry is probably the most specific. And I'm not going to go into this a little bit, but in terms of resolution, there's a lot of questions about resolution, and I think that people don't understand exactly what there is. There's mass resolution and there's mass resolving power. The resolving power refers to the performance of your instrument performance, and the mass resolution is your method-related performance. And I think people get those. They use them interchangeably, and they really shouldn't. And you can go and find out exactly what those are. There's IOPAC definitions, and I've talked about it in this chapter that I wrote a couple years ago. But I think there are some trade-offs. If you want to really have 100,000, 200,000 resolving power, you may have to give up sensitivity. And there's the argument for these higher mass resolutions may not really become persuasive until you're looking at things like proteins and things like that. So for small molecules, you actually may be able to get away with 20,000, 50,000 resolution and do very, very well in terms of discovery. And of course, the spectral acquisition rate that is required for these high resolving power instruments can be very slow. So on a chromatographic scale, if you have GC, good chromatography, and you're getting 1 second peak widths, and you need 1 hertz to get 200,000 resolving power, well, you're not going to really see much over that peak, right? So you have to, think about those things as well. So, resolution is great. You want as much as you can, but nothing comes for free. And I really think that, and if you are in the 20,000 to 50,000 range, you can probably get most of what you want to do done very, very well. I'd like, from the EU environmental point of view, there's this kind of this little table, and you can really start to think about specificity. The number of ions in an MS gives you a specificity point system. And you can see where MS and different types, flavors of that, so to speak, and how if you were to have even 3 ions with an HRMS system, you're still more specific than even MS with 2 precursors with 1 product ion each, which is very, very specific. So, you can kind of look at that. I like this little table, and I can really kind of say, okay, now I have something to think of, to point to when I'm talking about specificity in terms of my mass spectrum. And sensitivity, well, sensitivity is signal to noise. That's really what it's about, right? I got more signal, less noise. So you can do MS to mitigate noise. You can have high mass resolution to have very narrow ion extraction windows to mitigate that noise. And you can do QTOF and things like that I've mentioned. And there's a number of physical ways that the vendors do to mitigate these noise problems. You can get rid of neutrals, and there's lots of ways to do that. But really, sensitivity is signal to noise. And I think if you go to buy a new instrument, you look across the vendors, you're going to get some data spec sheet, and you're going to look at reserpine, and you're going to look at octafluoronaphthalene, and it's going to have some value, and it's going to be pretty much the same across vendors, because we can only go so low with the technology that we have, right? So we're all kind of hitting that vanishing zero kind of asymptotically. So I think, again, thinking about it from just these model compounds and specs point of view probably isn't the best way to look at sensitivity. It's about what can I measure, as I said, in my real samples with confidence and precision. And another thing about measuring the exposome, it's multiple chemotypes, and you will have to use multiple platforms. So if your lab is an LCMS lab, you may have to engage your environmental partner for ICP-MS information or something like that. So the exposome paradigm is something I love about it. It really offers the opportunity to collaborate with in an interdisciplinary way, and I really, really like that about that. So, if you want to measure these multiple chemotypes, you can do that. You can use all of these different tools. It all has to be fed into this bioinformatics. We have to have very strong, sophisticated bioinformatics. That's not my area of expertise. I'm not going to go into that too much, but that's really where making sense of all of this needs to be done. So that the data reduction and these algorithms, and they can compare lots of different molecules between controls and cases and various disease states, and these tools can help us pinpoint these the features that are interesting and significant in the models that we're looking at. And there are a lot of commercially available or freely available databases out there to kind of, okay, what are the known knowns in my sample, and what are the truly unknown types of things that I might want to, that might, at this point in time, all I have is a retention time, an accurate mass, and an abundance that seems to be important and pops up often in this particular case control set. So, how do you go about identifying that unknown that may not be in any of these things? That becomes an even much more complex problem. But there's lots of tools out there, and NIST is very large. Wiley NIST has nearly 900,000 compounds in it. Again, it's an EI type library, but screening against a library like that can be very helpful. So what does this all look like in the end? I know this is a very complicated little graph here, and I want to thank Shane Snyder from Arizona. But basically, you can kind of look at the targeted quantification, the non-targeted discovery type tools, and it all starts with your, from the targeted point of view, your sample. You do some type of extraction, isolation, your identification through mass spec, retention time, calculation of your recovery of your surrogates, data analysis using the bioinformatics or quantifying tools, and then you get basically your quantitative answers. And the tools that can be used for this are the LC-MS, GC-MS, ICP-MS. There's lots of ways to do this, and you can do this on a regular basis. The non-targeted discovery, for the characterization of these broader unknown compounds, again, it starts with your sample, but here we're going to get MS or MS-MS information that we need to use. We need to align, we need to extract the features, align, try to screen against libraries, do principal component analysis, things like that to try to understand exactly what we're seeing and what's important. And then, validation, if you're going to do MS follow-up studies, and then you can actually compound profile in a sample. And again, it's the similar tools. You could also do cell-based assays in this type of mode as well. So we really have a lot of, and it was said earlier, basically the tools and the workflows are kind of already there. We're just putting them into a new paradigm. So we don't have to do a lot of reinventing of the wheel. We just have to apply them into kind of some new types of new ways of looking at things. Oops. So then you can combine the two. And so this slide here just basically says, okay, if I want to do semi-targeted, which I want to be able to quantify a specific panel of compounds and interrogate that data for, for the unknowns and see if I can, determine features in that way, you can actually combine these two, and then you can use these types of instruments to do it. So you can look at it from targeted, semi-targeted, or non-targeted types of point of view. And I think you may get, in terms of semi-targeted analysis, where you might have access to MS, you can do scan MRM or sim scan type things. You have that could be very helpful, or scheduled type of MS processes. So I see my time is up, and I knew I would go a little bit long, but I don't have to talk about this too much, but basically what this is saying is that, with the data-driven LCQ-TOF, you are probably going to miss most of this curve here especially. So we have to kind of think about it from a blended point of view, or using semi-targeted approaches where I may get the bulk of this information here, but also use this type of tool, bring it all together in my bioinformatics. And then I can start to say, okay, I can really get that coverage along with this simultaneously. And the tools exist to do this, right? So, we can work in parallel on different platforms and then bring it together. And then, I think you'll get much broader coverage of the chemical space in this way. So these blended applications, you can see that, if this were the exposome space, LCMS, yes, it is going to cover a lot of that. And, electrospray positive, negative, reverse phase, HILIC, you're going to get a lot. GCMS will help. ICP-MS, you put those together, you really have covered a lot of the exposome space. And then, again, the key is taking all that, bringing it into bioinformatic tools to make sense of. So filtering for the normal variation from the unknown signals of interest, if we focus on the blood exposome, I think we can officially detect these exposures from both exogenous and endogenous sources, what Steve was saying earlier. And we need to do this from case control studies that have been nested from prospective cohorts collected longitudinally, if those exist. And I think the UK Biobank, I think, is one that may be doing that, and some others. So it's starting, and hopefully there'll be others to follow. We really need to have high mass accuracy, high resolution MS that gives us the specificity for most of these drugs, metabolites, dietary compounds. Good method protocols, and I'm going to go through those very quickly here, because I think it's important not only that you prepare your sample well, you pick the right platform, you make sure that your methodology is accurate, precise, sensitive, and specific. But then, should also, in terms of how do you run your samples, in terms of, collecting your data, creating a sequence or your run list, you want to, do some simple things. Randomize your case controls, block them within a fixed number of case controls between pool references and QCs. You want to use technical replicates of at least 3. And again, when you do this, we were talking about this earlier, you'll see that your detection improves because you're able to average over the technical replicates. So these are very important and very simple practices to do. And use from your platform and methodology type of techniques, use multiple techniques if you can, optimize chromatographic resolution, again, the high res. So just to sum it all up, detection is a composite of many things. So it's not just the detector. It really, and you have to kind of consider this holistic system if you want to get, good confidence in your data, repeatable data. So filtering the normal variation from the unknown signals that's of interest requires these measurements of performance and having confidence in them. And to overcome or mitigate these challenges, I think, just in closing, develop robust methods. If you have, often I hear, oh, I'm going to move to MSMS, or I'm going to, do QTOF. do less sample prep. No. Don't ever skimp on your sample prep. If that's what you do and that's what you need, do it and improve upon it over time. Don't skip on those kinds of things. Use these performance standards, blend platforms, et cetera. So I think with that, I'd like to thank Steve Rappaport and Shane Snyder, and thank you all.
So great, thank you. You mentioned sample prep, and also the speaker before mentioned sample prep. So that's bias, right? So we have to acknowledge and find bias. And you know, it's very hard for a investigator in analytical chemistry to publish robustness of methods and improvements and reliability tests, because analytical chemistry journal and other journals want the new detector, the new column, that ion mobility thing. But if you then say, well, if I use a different system, you know, my ions are 50-fold more abundant and it's actually good, you know, they usually say, well, that's not as novel using methanol instead of acetonitrile, say, right? So, no, we can't publish that. So it's a real problem even to publish these things in terms of robustness and reliability. But that's not the point I wanted to say. The point is, well, sorry. The point I wanted to say really is you elaborated a lot of still on the methods and NMR and GCMS and LCMS and so on. You did not elaborate as much on the sample prep and the bias, right? So if we assume now that most of our exogenous or xenobiotics are low abundant, and many of them might be lipophilic, they may hang with the proteins. You had one slide with protein crash. Well, maybe that's already the bias, yes, right? Because maybe what we'd need is a similar diversity of sample prep methods, including, for example, lipoprotein fractionations, and then see where these xenobiotics really hang in. And maybe that already tells us about biological function and response later on in time. If we do the protein crash, maybe that's the biggest mistake we can do. And yes, this is the regular metabolomics method that you find in all protocols, by the way. Yeah, so this is what I'd like to challenge all of us in the room here, you know, and I'd like to thank you to at least bring it up, sample prep, as the major bias. How can we do this all and still keep the costs low? Yeah. Because at the end of the day, if we do 3 technical replicates, 5 different methods, 5 different sample preps, and we have 10,000 samples, and we go to the NIH, we don't get the budget.
No, well, I agree that you know, the sample prep is very important. I didn't want to focus on it too much here because it was detection challenges, so I kind of wanted to focus on that. So, but there may be opportunities here for the rapid fire where you could actually do multiple cartridges and evaluate them kind of and have that information, do that as part of your method development where it's less costly, and say, okay, well, we've identified this as the best solution for this particular analysis that we want to do. So or you could, you know, on a regular basis, run 2 different types of cartridges and have that information. So the rapid fire could be helpful in that type of regard.
Hi, I'm Nate Snyder from Drexel University. So NIST makes a nice, useful reference human serum. Great for endogenous metabolites if you want to do workup for that. But nowhere in that reference serum is the average, like, exposed human being. If you want to standardize a field, you need some reference material. So it would answer your sample prep questions if you had the average exposed human being with known levels of POPs in there. Do your sample prep, see if different labs get the same answers, the same precision problems we've faced with a lot of endogenous metabolites. Yeah. Any interest in trying to put that together?
Well, I mean, I've heard people, and David might be able to help with this, but over time, I think we might find the baseline of the exposome. It's going to take you know, lots of measurements and lots of, because every one of us in this room has a different exposome, right? So we're going to have to figure out what's common in all of us and what's unique, and I think that will come with time and as the exposome paradigm grows, and more information is shared, hopefully in public repositories where we can all look at that type of information, then possibly we'll be able to find the baseline or average exposome, human exposome, and then move from there. But I think we're a long way from it right now.
The only question is, can I remember my question by the time that it get up here? Okay. Yeah. So some of these issues are fundamental with regard to the collection of samples and exclusion of samples, and one of them that I really have is about renal function, liver function, and so forth. Because if there's liver dysfunction, then there's different amounts of albumin in the blood. And of course, if the albumin is binding these chemicals, then there's an association with the amount of albumin you have. And similarly, if there's any renal dysfunction, which there is with aging, there's going to be changes relative to that. So do you have thoughts on how we deal with those types of challenges?
Short answer, no. I haven't thought that far ahead yet. I think I'm still an exposome neophyte and hoping to do some of these things. And I think these questions will be answered. And you obviously have them, so they will be answered. And yeah, absolutely, I think that they're going to be important. And if there's ways where we can actually leverage what we know, physiological changes that occur with albumin and with renal clearance, things like that, and we can correlate those with the exposome, then there'll be great opportunity there as well to kind of understand chronic human disease in a better way.